Okay, so welcome back to another video. So this time, let's try to solve the entire cycle of a diesel cycle. Okay? So the first thing that you need to do, or the step one first, is for you to label your PV and TS diagram. Of course, you need to draw it first. So let's label it from what we did in the previous video. We've said that from point 1 to 2, that is isentropic. 2 to 3, that is constant pressure or isobaric. This one is isentropic, and this one is isochoric process. Next, heat addition. Heat addition takes place at point 3, 2 to 3, and heat rejection is from 4 to 1. Okay? So let's write down our given. So there are supplied 317 kilojoules per cycle. So that supplication is heat addition. That is 317 kilojoules per cycle. So we only have one cycle. So therefore, kilojoule per cycle times one cycle. So cycles will cancel out, leaving us with kilojoule. To a diesel engine operating at mass, we have a mass of that is in grams, so therefore we need to convert that to kilograms. Then of air, so we know that R is 53.34. So since this is in SI, so it should be 287.08 joules per kilogram Kelvin. Okay, so P sub 1, or the suction pressure, that is P1, is equal to 97.91 kilopascal. And then T sub 1, that is equal to 48.9. So that is 48.9 plus 273.15. So equal to 322.05. 0.05 Kelvin. And at the end of compression, so that is 0.2, the pressure is now 3,930 kilopascal. So we are asked to determine the several factors, but for your convenience, so let's try to solve P, V, and T in all the points of the cycle. So we will solve P1, P2, P3, P4, so as V1, P2, V4, etc. Okay? So let's start first at point number 1. So in point number 1, we are given P1, T1, we are given R, we are given M. So since we are given P1 and T1, we can solve for V sub 1. So that is letter A. Okay, so letter A, that is V1 is equal to MR T sub 1 over P sub 1. So M, that is 0.227 kilograms times R of 287.08 joules per kilogram Kelvin times temperature, that is 322.05 Kelvin over P sub 1, that is 97.91 kilopascal, or that is kilonewton meter squared. Okay, so joules here, let's expand this as Newton meter. So as you can see, kilogram will cancel, Kelvin cancels, and Newton cancel out, leaving us with V sub 1 is equal to, so that is 0.227 times 287.08 times 322.05 divided by 97.91 kilopascal. So that is 0.2143. 2143. So that is in cubic meter. Okay. Next. So now that we have V1, so the next thing that we can solve is I have P2 and P1, and I have T1 as well. So I can solve first for T2. So that is T2 over T1 is equal to P2 over P1 quantity K minus 1 over K. So that is your isentropic relation. Because from point 1 to point 2, in order for you to reach point 2, you need to subject the fluid into an isentropic process. So therefore, you need an isentropic relation. So T sub 2 is equal to T sub 1, that is 322.05 quantity. P2, that is 3,930 kilopascals over 97.91 kilopascal raised to, so K of air, that is 1.4 minus 1 over 1.4. So T2 is equal to, let's plug it in our calculator. We have 322.05 quantity 3930 divided by 97.91 kilo raised to 1.4 minus 1 over 1.4. So T sub 2, that is 924.878. 878. So that is in Kelvin. Okay. Next. So I have T sub 2, I have P sub 2, I don't have V sub 1 yet. So how am I going to solve for V sub 1? So I can use the isentropic relation T2 over T1, that is V1 over V2 raised to K minus 1. Okay? So here, I need to solve for V sub 2. So what I'm going to do is that I will flip this this variable, the base of the right side. So if I flip the base of the right side, in order for the equation to be balanced, I need also to flip the base of the left side. So I will have T1 over T2 is equal to V2 over V1 quantity K minus 1. Okay? So if I isolate V2 here, so V2 will be T1 over T2 1 over K minus 1 times V sub 1. Okay? So I can substitute directly the variables. So I have T1, that is 322.05 over T sub 2 of 924.878. So the Kelvin here will cancel out. 1 over 1.4 minus 1 times V1, that is 0.2143 cubic meters. Okay? So Kelvin will cancel out. So the final unit is cubic meters. So I have V sub 2. So by observation in our PV diagram, volume 2 should decrease. Okay? From point 1, it should decrease. So I have quantity 322.05 over, so that is 05 over 924.878 raised to 1 over 1.4 minus 1 equals, and then times 0.2143. So I have V2 of 0.0153 cubic meters. Okay? So that is V sub 2. So we have V2, T2, P2. So point 2 is already finished. Okay? So let's proceed to letter C. So let's answer first letter A. Okay? So we are asked to solve for the compression ratio. So that is letter D. So since we have V2 and we have V1 as well, so I can solve for the compression ratio. That is given by V1 over V2, or simply our V1 is 0.2143 cubic meters all over V sub 2, which is 0.0153 cubic meters. So I will have compression ratio is equal to, so that is 0.2143 divided by the answer, that is 13.97, or simply the compression ratio is 14. Okay, so let's put the box around it since it is a required variable. Okay, so compression ratio is okay already. The next one is the clearance percentage, so letter E. So now that we have our compression ratio, we can solve for the clearance percentage by using this equation, 1 plus C over C. So actually you can use shift solve here, but for your convenience, let's try to derive. So let's cross multiply. So we have RK times C is equal to 1 plus C. So separating C on the left side, we have RK times C minus C is equal to 1. So we can factor out C. So C quantity RK minus 1 is equal to 1. Okay, so let's divide both sides by RK minus 1. We have C, or your clearance, that is 1 over RK minus 1, or 1 over 14 minus 1, or simply 1 over 13. So our clearance is, so that is 1 divided by 13, so that is 0.0769, or simply this is approximately 7.69%. Okay, so let's put a box here. So let's rewrite this one. So 7.69%. Okay, so the clearance is already okay. Next, so since we are done already with point 1 and point 2, we can now proceed to point 3. So that is letter F. So here we will relate point 2 with point 3. So their relationship is an isobaric process. So the first thing that we can conclude there is that P2 is equal to P3. Okay? Because P2 is already given in the problem, which is 3,930 kilopascal. So therefore P3, we can conclude that P3 is equal to 3,930 kilopascal. Okay, so that's our conclusion. Next, so letter G. So we can use combined gas law, which is given by P2 V2 T2 is equal to P3 V3 T3. Okay, so since that the pressure is constant at that point, therefore pressure will cancel out, and then we can perform separation of variables. We have T3 over T2 is equal to V3 over V2. So as you can notice, V3 over V2 from our previous video, that is your cutoff ratio. So we can conclude in this equation that you can also solve for the cutoff ratio by dividing T3 over T2. However, we cannot use this one because we don't have yet T3 and we don't have yet V3. So we have one equation and two unknowns. So therefore we cannot solve that. So what we can do is that we can manipulate the heat equation. So we have QA. So since we've said that it is added during constant pressure, as you can see here, it is added at constant pressure, the equation of heat should be QA is equal to mCp T3 minus T2. So if we isolate T3, so let's divide both sides by mCp and then transpose T sub 2. Okay, so we have T3 is equal to Q over mCp plus T sub 2. So the only thing that is unknown here is CP. But CP can be solved using KR over K minus 1. That is 1.4 times 287.08 over 1.4 minus 1. So CP here is 1004.78 joules per kilogram Kelvin. Okay, so if you want to verify, so we can do that. So 1.4 times 287.08, so divided by 1.4 minus 1, so that is 1004.78. Okay, so now we can substitute our known values in the equation. QA, that is 317 kilojoule over the mass which is 0.227 kilogram times 1004.78 joules per kilogram Kelvin plus T sub 2, that is 924.878 Kelvin. So joules, kilograms, leaving us with Kelvin. So T sub 3, that is equal to 317 kilo divided by 0.227 times 1004.78 plus 924.878. So we will have 2,314. So that is 2,314.71 Kelvin. Okay, so we have the temperature. So next thing, so we've concluded here that we can solve for the cutoff ratio by dividing T3 over T2 as well, alright? So in letter, what letter are we now? G. So letter H. So RC can be solved by V3 over V2 and also can be solved using T3 over T2. So since I have T3 and T2 as well, so I just need to get the ratio of that for me to solve cutoff ratio. 0.878 Kelvin. So let's divide this. We have the cutoff ratio of, so we have the cutoff ratio that is divided by 924.878. We have the cutoff ratio of 2.5. Okay, so this will be our cutoff ratio. So now we have the cutoff ratio. We can solve for, so let's put a check first in the cutoff ratio. Okay, we can solve already for V sub 3 because cutoff ratio is V3 over V2. So therefore V3 is equal to V2 times the cutoff ratio, which is V2 is equal to 0.0153 times RC, which is 2.5. So V3 is equal to, so we have 2.5 times 0.0153. So we have 0.0382. 382, that is in cubic meters. Okay, so we have V3, we have P3, we have T3, so we're done already with point number 4. So let's proceed with the next step. So we're done with point number 3, so we'll proceed to point number 4. So from 3 to 4, so this one, we need to undergo, or the fluid needs to undergo an isentropic process. So we can relate each other. So I want to solve first for T4 over T3 is equal to, so let's solve first for T4. That is V3 over V4 raised to K minus 1. So as we've said, in diesel cycle, what you can notice in V4, it is the same as V sub 1. So we can conclude here that V4 is equal to V1. So we can substitute that here. So we have T4 is equal to T3 quantity. So V3 we have this one, 0.0382 cubic meter over V4, that is equal to V1, which is 0.2143, if I'm not mistaken, 2143 cubic meters raised to 1.4 minus 1. So we have T4 is equal to, so let's substitute T3. So we haven't yet substituted T3 here. So T3 must be 2314.71 Kelvin times 0.0382 over 0.2143, 1.4 minus 1. So T4 is equal to, that is 2314.71 times 0.0382 divide by 0.2143 raised to 1.4 minus 1. So we have the temperature, that is 1161.216 Kelvin. Okay? So that is T4. What about, so letter K. So what about P4? That is P4 over P3 raised to V3 over V4 raised to K. So P4 is equal to P3, that is equal to 3,930. So kilopascal. Quantity V3, that is 0.0382 cubic meters over 0.2143 cubic meter raised to 1.4. So P4, so based on our PV diagram, P4 shall be less than P3. Okay? So if you compute a value that is greater than P3, so immediately you need to verify your answer. So you need to double check that. Okay? So that is 0.0382 divided by 0.2143 raised to 1.4. So that is 351.439 kilopascal. Okay? So for separate section, let's just put letter L here, wherein we conclude that V4 is equal to V1, wherein V4 is equal to 0.2143 cubic meters. Okay? Next. So now we have this one. We have pressure, volume, and temperature at point 4. Let's now solve for heat rejection. So heat rejection is given by negative mCV, that is T4 minus T1. So we don't have CV yet. So we can solve for CV, that is R over K minus 1. So R, that is 287.08 over 1.4 minus 1. Or simply CV is equal to 717.7 joules per kilogram Kelvin. Okay, so if you want to verify, so we have 287.08 divided by 1.4 minus 1. That is 717.7 joules per kilogram Kelvin. Okay, so if we substitute everything to the equation, we have QR, that is negative, mass is 227 kilograms times 717.7 joules per kilogram Kelvin times T4, that is 1161.216, minus T1, that is 322.05 Kelvin. So we have kilogram, Kelvin, cancel out. So we have QR, or the heat rejected, that is equal to negative quantity 0.227 times 717.7 times 1161.216 minus 322.05. So we have the value of heat rejected, that is negative 715 kilojoule per cycle. Okay, so it is per cycle because heat addition is given by kilojoule per cycle. Okay, so now that we have QR, so let's proceed. Letter N, we can solve for work net. So work net is QA minus QR, which is given by QA, that is 317 kilojoule minus 136.715 kilojoule. Okay, so the work net is equal to, so we have 317 kilo minus 136.715 kilo. So that is 180.285 kilojoule per cycle. So I believe this is a necessity. So that is work net. So we need to put a box around it. Next. So in letter O, we forgot something. We should also solve for the expansion ratio of the system, that is given by V4 over V3. V4 is 0.2143 cubic meters all over V3, that is 0.0382 cubic meters. So we can cancel this one. We have the expansion ratio is equal to 0.2143 divided by 0.0382. So that is 5.6. Expansion ratio is 5.6. Okay, so actually you can solve for the expansion ratio because we said that the compression ratio is the product of RC times RE. Okay, so we can solve for the expansion ratio by dividing the compression ratio by RC. So if we divide that, our compression ratio is 14 divided by 2.5, so that is 5.6. Okay, so we have obtained the same value, the expansion ratio. Next, so letter P. So in letter P, since we have the work net, we can solve for the engine's efficiency, which is given by work over QA. So work is 180.285, so kilojoule per cycle, over QA, that is 317 kilojoule per cycle. So as you can see, kilojoule per cycle will cancel out, leaving us with the efficiency is equal to, that is 180.285 divided by 317. So that is 0.5687. 87, or approximately 56.8%. Okay? So we can double check this one by using the simplified equation for efficiency, which is E is equal to 1 minus 1 over RK raised to K minus 1 quantity RC raised to K minus 1 over K RC minus 1. Okay, so we have 1 minus 1 over 14 raised to 1.4 minus 1 quantity cut off, that is 2.5 raised to 1.4 minus 1 over 1.4, then RC, that is 2.5 minus 1. So if you input that in our calculator, we will have, let's try 1 minus 1 over 14 raised to 1.4 minus 1. Then 2.5 raised to 1.4 minus 1 divided by 1.4 times 2.5 minus 1, then equals, so it is 56.8, so that is 0.568, or approx, that is 56.8%. So regardless of the process that you used, the equations that you use, you should arrive with the same magnitude. Okay, next, so now we have obtained the efficiency, so let's put a check. So now we can solve for the volume displacement. So for the volume displacement, that is given by V1 minus V2, and V1 is given by 0.2143 cubic meters minus V2, that is 0.0153 cubic meters. So the volume displacement is equal to, that is 0.2143 minus 0.0153. So the volume displacement is 0.199 cubic meters. Okay, next, so for the last one, so we can solve for the mean effective pressure, that is given by work over volume displacement. So the work is given by 180.285, so that is in kilojoule, over volume displacement, that's 0.199 cubic meters. So meters and meter cube will cancel, leaving us with meter squared, leaving us with the mean effective pressure of, that is 180.285 kilo divided by 0.199. So that is 905.954 kilo Pascal. Okay, so we've already solved for the entire cycle. So my tip when you are solving for gas cycles is for you to try to solve each point. So you solve for point 1, point 2, point 3, point 4. You should not limit yourself with the variables that are necessary. Okay, it's okay for you to solve for that. So once you're done solving for all those variables, you can check using, or you can check by consulting your PV and PS diagram. So if the PV diagram says that the pressure shall increase, so the variable that you have computed should increase. Okay, so it should satisfy as well the graph. not only in the PV diagram but also in the TS diagram. Okay, so I hope we obtain with the same answers or the same magnitudes of these parameters. So in the next video, we will discuss dual combustion cycle. So we will derive also equations pertaining to dual combustion, and then we will answer sample problem. Okay, so I hope you've learned something in this video. So thank you for watching, and God bless us all.